Get this party started. Edmund of Code 2024, day 22. It's called Monkey Market. As you're all teleported deep into the jungle, a monkey steals the historian's device. You'll need to get it back while the historians are looking for the chief. A monkey that stole the device seems to be willing to trade it, but only in exchange for an absurd number of bananas. Your only option is to buy bananas on the monkey exchange market. You aren't sure how the monkey exchange market works, but one of the historians senses troubles and comes over to help. Apparently, they've been studying these monkeys for a while and have deciphered their secrets. That's lucky. Today, the market is full of monkeys buying good hiding spots. Fortunately, because of the time you recently spent in this jungle, you know lots of good hiding spots you can sell. If you sell enough hiding spots, you should be able to get enough bananas to buy the device back. Perfect. On the market, the buyers seem to use random prices, but their prices are actually only pseudo-random. If you know the secret of how they pick their prices, you can wait for the perfect time to sell. The part about secrets is literal, the historian explains. Each buyer produces a pseudo-random sequence of secret numbers, where each secret is derived from the previous. That's how they work. In particular, each buyer's secret number evolves into the next secret number in the sequence via the following process. Calculate the result of multiplying the secret number by 64. Mix this result into the secret number and prune the secret number. Presumably, you'll tell us what mix and prune mean. Calculate the number of dividing secret number by 32. Okay, so we're just doing power of 2. We're doing bit shifting. Round the result down to the nearest integer. Okay, so we're doing integer bit shifting, yep. And then mix this result into the secret number and finally prune the secret number. Calculate the result of multiplying by 2048. Okay, and then mix and prune. Got it. Here's mix and prune. Bitwise exclusive OR of the given value and the secret number. Then the secret number becomes the result of that operation. All right, so we multiply by 64 and then do an exclusive OR with the previous value. Okay. To prune, we do mod this number, which is a power of 2 again. Got it. After this process completes, the buyer is left with the next secret number in the sequence. So the buyer can repeat this as many times. Buyer has a secret number of 123. Then we have this sequence. Each buyer uses their own secret number when choosing their price. So it's important to be able to predict the sequence of secret numbers for each buyer. The initial secret number of each buyer is your puzzle input. Okay. This list describes the initial secret number of 4 secret hiding spot buyers. A single day, the buyers have time to generate 2,000 new secret numbers. Okay. Adding up the 2,000th new secret number for each buyer produces this number. For each buyer, simulate the creation of 2,000 new secret numbers. What is the sum of the 2,000th secret number generated by each buyer? All right. That I'm missing the trick, I think. And I'm thinking, well, okay, maybe part 2 is generate, 2 trillion. And then you figure out there's a loop in there. Although modulo this number is pretty big for a loop. All right, I'm not going to worry about part 2. Let's worry about part 1. Let's get our input. There's 2,240 lines of secret numbers. Okay, so maybe that's where the complexity comes in. I'm thinking, because this is just pseudo-random, we can just create like an iterator. Which just gives us the next value in the sequence. Let's create a struct secret, which is, looks like we only need, what is this? Is this 24 bits? I don't know how many bits this is. It's 20, then 2, 4, 6, 8. No, 2, 4, 8, 16. Yeah, 24. So it's 24 bits. Okay. So if we did, let's say a U U32 should work fine. Let's see if that works. And then we'll have a impl from stir for secret. And implement the missing members. It's going to always work. And we're going to say OK. Self parse unwrap. I think that'll work. Let's find out. And then we're going to have a vector of secrets here. Secrets is a vec of secret. And then parse is going to be let lines equals islib read lines of the input, and self secrets is equal to lines iter map line parse unwrap collect. That should give us all the secrets. Let's print them out. I like to do that when I'm doing these things. Didn't like that because we can't debug. Let's debug. Yeah, and now so we have all these secrets. So 2171043 is the first one, and then the tail, let's just check, is 137. Yeah, that number right there. Okay, so we have them all. Always good to double check. Then let's impl iterator for secret. No, the way you implement iterator is you create an iterator on it. Can we just do it directly though? Let's find out. I was thinking I would have to create a secret iterator struct, but I don't think we have to store any information other than what's in the secret. So it might be possible to just do it this way. Item is equal to self. And we always get the next value. So let's see. Here's the whole thing. Multiply the secret by 64 and then mix, which means do the bitwise exclusive OR and then prune. Okay. We can prune at the end. We don't need to prune in the middle because we're always doing we're doing bit shifts and stuff. We can ignore everything until we get to the end. Because we can say, oh, let me just do it step by step. So we're going to say let self step 1, right? This will be step 1, step 2, and step 3 here. Step 1 is going to be self.0 shifted by 6. Right? We can just say multiply by 64. The compiler will fix that for us. And mix that result into the secret number, so exclusive void with self.0. And then prune it, which we can do at the end, because it's all power of 2 stuff. Step 2 is going to be step 1 multiplied by 32. Round down to the nearest integer. Oh, divided by 32. And then mix. Oh, that's why we need to prune, because we're going to shift the values down. Okay, so we do need to prune here. So this will be, it should figure this out too, right? It should figure this out that this is a bit shift operation, or an AND operation. I don't think we're going to have a problem. And then step 3 is equal to multiply by 2048. 2048. And then mix, not self-zero here. Step 1. And this is step 2. And again, mod this number. And that's it. And then that's our self-zero is equal to step 3. Return some step 3. And I'm seeing syntax errors. Why? Expected a name. Oh, mod. Sorry, I was in a different language. Step 3.0. No, that's right. Step 3. Oh, it has to be a secret. So some self. No. Some self. No, because now we have to copy it. We can just go clone. Okay. All right, that works. So now we can iterate and get the 2000th number. Adding up the 2000th new secret number for each buyer. So this should be part 1, right? So we could say total is equals to self secrets. Iter map secret iter nth 2000 sum u32. Didn't like any of that. Oh, because yeah, u32 like that. Okay. I don't know if that's going to work, but we can do it with this code here. Test mod test secret 1, just to make sure we have the right value here. Let secret is equal to secret of 1 iter map, no, iter nth 2000 unwrap, I think. Oh, I might have to unwrap it here as well. No, it didn't complain. It just said nth 2000. Does that return? Let me make sure I took out that print statement. Okay. And this won't build because of this. Let's flip over to test here. And this should be this number. So we're expecting this, and the actual is secret 0. Oh, interesting. Why is that I32? Oh, maybe this should yield a U32. That way I can just say step 3 here. Right? It's just returning the value. That's all we care about. Can I just say nth 2000? Oh. Okay, we're going to have to play around with this a little bit. Cannot be made by summing this item as option U32. So we do need to unwrap it here. And then this is total. You may want to use iter mute here. I do, because I do want to modify it. Okay, so we have to do the same thing down here. But it won't let me do that. Method not found in secret. Really, but it took it here. If I hit run, it panicked. Attempt to multiply with overflow on line 57. Oops. Oh, okay. So maybe we don't want U32s. We want U64s. Because we shifted beyond the length of the... Oops. So this needs to be U64. All right, we got a value. How come I can't do it here, though? Maybe I have to say let secret is this, and then say let 2000th is equal to secret, and this is 2000th. Test. Huh. Why is it? Oh. Okay. I can just say nth on this guy. There we go. And I'm getting the wrong value. Do I need to do 2000? I'm glad I did a test then. Do I have to go 2001? No. 2000, maybe 999? Yeah. Okay. So that's what I need to do. And now if I run this, we get this number. Yeah, that's the right answer. That was surprisingly easy to do. Let's see what Clippy says. Clippy likes it. All right. So I didn't need to create a separate iterator for that. Iterator struct. We're just modifying the struct on its own. I guess I could. If I did an iter, well, I'm not going to worry about it. Okay. Git status. Git add source. Git commit dash 2024 day 22 part 1. Okay. That was easy. How long did that take? Continue to part 2. Of course, the secret numbers aren't the prices each buyer is offering. That would be ridiculous. Instead, the prices the buyer offers are just the ones digit of each of their secret numbers. Oh, so if a buyer starts with secret number of 1, 2, 3, that buyer's first 10 prices would be these values. Okay. This price is the number of bananas that the buyer is offering in exchange for your information about a new hiding spot. However, you still don't speak monkey. So you can't negotiate with the buyers directly. The historian speaks a little, but not enough to negotiate. Instead, he can ask another monkey to negotiate on your behalf. Okay. Unfortunately, the monkey only knows how to decide when to sell by looking at the changes in price. Specifically, the monkey will only look for a specific sequence of 4 consecutive changes in price, then immediately sell when it sees that sequence. Sorry. So if a buyer starts with a secret number of 1, 2, 3, that buyer's first 10 secret numbers, prices, and the associated changes would be this. Right, so these are the numbers that we come up with. Then we take the ones digit, and then we do the delta. So this goes from 3 to 0. This goes from 0 to 6, 6 to 5. Okay. Note that the first price has no associated change because there is no previous price to compare it with. In this short example, with just these first few prices, the highest price will be 6. So that would be nice to give a monkey instruction that would make it sell at that time. The first 6 occurs after only 2 changes. So there's no way to instruct the monkey to sell then. But the second 6 occurs after these changes. So if you give the monkey that sequence of changes, it would wait until the first time it sees that sequence and immediately sell your hiding spot information at the current price, winning you 6 bananas. Perfect. Each buyer only wants to buy one hiding spot. So after the hiding spot is sold, the monkey will move on to the next buyer. The monkey never hears that sequence of price changes from a buyer. The monkey will never sell and will instead just move on to the next buyer. Okay. Worse, you can only give the monkey a single sequence of 4 price changes to look for. You can't change the sequence between buyers. You're going to need as many bananas as possible, so you'll need to determine which sequence of 4 price changes will cause the monkey to get you the most bananas overall. Each buyer is going to generate 2,000 secret numbers after their initial secret number, right? So we've already gone through that. So we need to undo that and change things. Okay. For each buyer, you'll have 2,000 price changes in which your sequence can occur. Suppose the initial secret number of each buyer is this. For many sequence of 4 price changes, you could tell the monkey, but for these 4 buyers, the sequence that will get you the most bananas is this. All right, so we need to find something that'll find this sequence. And then what's the most bananas you can get is our answer. And it looks like for this, we'd get 23 bananas for this sequence of prices for these 4 secret numbers. Oh, all right. So I think what we need to do is collect all of these instead of just getting the 2,000 entries. We need to collect them all and then do deltas on the ones digit. And in general, I'm not a fan of making part 1 and part 2 dependent on part 1. I've said this before, but here we are. Maybe parse can be get this first 2,000, and then part 1 will be sum up the last, and then part 2 will be okay. Let's see if we can work it that way. So we're going to say prices is a vec of I64, U64. We're going to say this. We're going to say type price is equal to U64. That way I don't keep changing it. Right? That should still work. Right? We're not using prices yet, but we're going to do it here. We're going to say, after we collect all the secrets, we're going to say for secret in self secrets iter mute. I guess we could just do it this way, right? We don't actually need the secrets after we've gotten the values for them. So we can just say, do this, let mud. Right? And then we can say for secret in secrets, prices dot push secret dot take 2000. Oh, the reason, right. The first one is not yielded here. We don't get the first value. We have, and which we need. All right. Let right, because we need to get the sequence of numbers, and it needs to start with the first price of 1, 2, 3. So, and that's why we had to do nth 1999 is because we weren't including the first number there. Okay. We'll call it a list is equal to secret dot 0, and then say list extend secret take 1999, and then push list. Will Rust let me do that? Self prices push. No method name extend. Oh, vec. Right, this has to be a vec. With this guy. Right, now what we just need to do is look at the last one. Total secret. No, this is prices. It's self prices map list last unwrap some price. Iter map. And that's wrong. That's the wrong number. Oh, right, because we do need to get 2,000 of these out. Yeah, and I think that's the right number. I remember it starting with 18. 1869 and ends in 6361. Okay, so we haven't broken part 1 yet. Let's commit this. Oh, it doesn't like... Oh, because it doesn't need to be mutable. It's the secret itself that needs to be mutable. Okay. And Clippy's good. Okay, git status, git commit -am refactor for part 2. And now we just need to collect in part 2, we need to collect all the deltas of the digits. So we're going to say, we're going to create sequences. And how do we do that? We're going to say let sequence is equal to vec new for price in self prices. And this should be a vec of U64s, right? And now all we need to do is get the ones digit and save the deltas. Or we could be smarter. We could say let, let's call it seeks. Seek is equal to price dot Windows 2 dot map. I think it's pair, like that. And we can say pair of 1 minus pair of 0. Collect. And then seeks, push, seek. Oh, we have to tell it it's a vec. Like this. Okay. Expected. Oh, yeah, because I didn't do this. Okay. Oh, right. Now we have a problem because these are all U64s. Let's change them to I64s. All right. So now we have a bunch of sequences. And now what we need to do is figure out which sequence will give us the highest value. So let me just print out one of these guys and make sure we're getting actual sequence of that works. Oh, right. This should be mod 10, right? Like that. And then we can print out seeks of 0, say. Yeah, so this is just a bunch of sequences of numbers of price changes, of single-digit price changes. So now we have to collect up all of the possibilities and then find out what the cost is given that possibility. So we can use Windows again, but Windows 4, because it's a sequence of 4. It's a sequence of 4 price changes. Yeah. Do we stick that in a hash set? I think we do. And we can actually grab it from here. So we can just say let what do we want to call it? I don't want to call it sequences again. Let's call this delta then. Let's change this to deltas. Oops. And change this to delta. Right? And then we have sequences. There's a hash set new. Oops. And then for each one of these, we don't actually need to save them if we're just, oh, no, we do. Because we need to know the index at which we're doing that. Okay. So sequences dot, no, we can say for quad in Delta Windows 4. Oops. And this should be, a reference to I64. So I don't know if we can do that. Sequences dot insert quad. I don't know if it'll let me do that because it's going to be a reference to something that's going away. Yeah. So we might have to clone these in here. No? Barred value does not live long enough. Right. We're moving out of delta, but that, okay. Do I need to do it this way? Quad 0, quad 1, quad 2, quad 3. Each one of these should not be a reference. These should all be direct values. Oops, need to do that. Right? Yeah, so now it copied it out. It took a while. I don't know if you saw that. It took a little while to run. How long did that take to run? 1.6 just to collect all the data. We're allocating a lot of memory. But now we have all the sequences of 4 price changes. We can find out how many of those are. Sequences.len. How many of those are there? 40,000, 41,000 sequences. So now we have to go through each of the sequence. Oh, it's going to take a while to run, isn't it? Let's flip over to test, and that way we can test this business here. Test part 2. Let's split out the parse into, yeah. Let's grab this code here and put it separate so we can actually test it. fn build secrets itself secrets. It's a vec of price, a vec of secret. Right, and then we can just say build, self-build secrets. That. I can clone the value and consume it. And why was it letting me do it here and it wasn't a problem? Can I just say mute like that? No. Do I have to make that mutable? No? Like that. There we go. Okay. And now what we can do is just pass in these secrets here, right? We can just create these 4 secrets. To secret 3 and secret 2024. And then we can say let AOC equals AOC default. AOC build secrets, right? That should all compile. And then we're looking for 23. AOC bananas. And then we'll extract this out into bananas. Returning a price. No, returning a use size. Because it's the number of bananas we can get. What's the bananas? Because these are the prices. Oh, and then this is the number of bananas you can get from that. Okay, all right. So let's, I guess we could just call it a price. No, yeah, price. It's just to keep things simple. It's kind of weird saying that we're returning it as a price, but okay. Self bananas. Let's just output that. And right for now, we're just going to return 0. Okay, so now we now have all the deltas. We now want to walk through all of the sequences that we have in deltas to determine, oh, we do want to store it. Okay, it's not as easy as I thought this would be. Because we don't want to just store the deltas. We need to also store the prices for each one. But we have that, right? In self prices, we can get from that. As long as we know the index, we should be good. Okay, so we can say for seek in sequences. Yeah. So we're going to go through every set of 4 entries, and we're going to look in the deltas here to figure out what index that is, and then look up the price here. Okay. For delta in deltas. And this should be a vec of I64. And now we're going to find, when we say delta find seek, I don't know if that'll work. And I always find the monkey always does it as soon as it sees that sequence, right? Unknown. It's a vec. I thought we could do a find on a vec. No method named find. Do we have to iterate? No. Maybe we do. Iter find? And we get an option of I64. That's not what I want. I want the this takes a closure. Really? Searches for an element of an iterator that satisfies a it has to be a single. Okay. So can we say Windows 4? Enumerate. Find X. What is X? The type of X now? It's a U size and an I64. And we want to compare it to SEQ, seek. And then return that index, right? What is this going to be? Option U size I64, and we don't care about the first part. Some index underscore equals. If we found it, then we have the index at which we found it, which means we're looking for the price. Let's see, we're looking for -21, -1, 3. Oh, using that set. Here, we're looking for this, -1, -1, 0, 2, and that's a value of 6. So we're going to return this index. So we just need to add 3 to get the value of the bananas. So we want to say quad. So quad 0 is equals seek 0 and 1 is 1, 2 is 2, and 3 is 3. Then, if that's true, then we want to say and we're going to grab the index in that. Oh, shoot. We do need to know which one we're in. So we're going to say which and delta, and delta's iter enumerate we're going to say self prices of which plus 3 mod 10. Right? That's how many bananas it is. The highest price will be 6. Oh, so we're getting... Okay. Yeah, I think we're just adding those up. The buyer with the initial secret number of 1 that changes -2, 1, -1, 3 first occur when the price is 7. Okay. So we'll see. Total plus equals this as U size. And then break. No. We only care about the first one. Oh, yeah. That's fine. And we care about the maximum that we can get. So max is equal to max total. Max. What is this? Oh, price dot 0. Oh, really? So price is a vec of I64 Global? That's true. Oh, no. Prices of which of index plus 3. There. Ah, I'm off by 2. All right, let's see which ones we're finding. Println seek equals total. Oh, that's a lot more in the test than I thought there would be. Oh, because we're doing 2000. Okay, let's output this here. Cargo run less, and we're going to look for the sequence of -2, 1, -1, 3. Wow, okay. Lease to out. Oh, even in release mode, it's slow. Oh, because... Sorry, I'm doing that. Test. And what did I call this test? Test part 2. That's a bad name for it. Test. Let's call it test for monkeys. Okay, so it was -2, 1, -1, 3. -2, 1, -1, 3. Which came up with 14. That's not good. Okay, so let's find out why it came out with 14. It should have been 7, 7, 0, and 9. And so we can actually save all that information. Values push this. Let's look. It came up with 4, 4, and 6. So maybe this index plus 3 is wrong. It should be. Well, let's see what those values are. I don't want to print out every single one. I mean, I can try index plus 4 and see what happens. There, 7, 7, and 9. Still the wrong answer. So where's it coming up with 25, I guess? Let's look for 25. Oh. 5, 4, and 4 does not equal 25. Oh, because I forgot to do this. Okay. All right, it passes. So that was the bug. All right, we don't need to do this anymore, or this, but it's very slow. It's very slow. But we might have, it might be done at this point. Oops. We can try it. Cargo run, release. Yeah, this is excitingly slow. How else would we do this? What would be, because we're only trying each sequence of 4 once. Is there a way to is there a way to speed this up, because this is painful? I mean, right? I mean, we need to look at the sequence of 4. We need to find it in each of our deltas. We need to add them all up. I wonder, well, I mean, what we can do is see what's going on. All right, we could do that, cargo run. We could also try doing it in multiple threads. It's getting somewhere. We can try a bunch of these numbers as they come through. It has to get through 40,000. There's a couple more. I'm gonna let this keep running over here because eventually it's going to finish. Let's see which sequence we're in. Let's see how slow this is going. Nope, it came up with 2100. And it's the right answer. Would have been very surprised if it was wrong at that point, but wow, it is slow. It took 145 seconds to come up with that. Yeah, and going through 41,000 sequences. Maybe maybe what we can do is keep track of how frequent that sequence is and go by the ones that happen most to least, because the ones that happen most should happen more often, which means we want to change this from a hash set to a hash map.